Hello everyone. In this video we are going to talk about a specific category of mobile robots called differential drive robots that are kind of the most common one because of the ease in basically estimating and controlling their pose. And what these robots are, typically there are two driving wheels and there is one or two caster wheels that is not driven and just used for static stability. And based on the difference in the rotational velocity of these two tires, right and left, you can basically maneuver the robot, move it forward, backward, steer it left, steer it right, and so on and so forth. That's why we call them differential drive, and we'll see that in the governing equations right now. So here I have an inertial frame xi, yi, and here we assume that the motion of this robot is pure in xy plane. So we are looking from the top view. We also attach this frame xr and yr to the robot. So this xr, yr is body attached. It is at the centroid and it does rotate with the robot chassis. X is in the direction of motion and y is perpendicular to that such that z is out of the plane. So y is going to be from right tire to the left tire. If we consider the velocity of the centroid to be v in general, and the linear velocity of the centroid is called v, and the angular velocity of the chassis to be called omega. Then based on v and omega, we can determine the change in the x, y, and theta coordinates of the robot. So x and y are the coordinate of the centroid of the robot in the inertial frame. So this is x, this is y. And theta is the angle between the body attached xr and the inertial xi. Right, in a counterclockwise manner measured positive, we call it theta. So this robot has 3 degrees of freedom, definitely x, y, and theta. These 3 parameters would determine basically the degrees of freedom of the robot in the workspace. And so when we say pose of the robot, we really mean the set of these 3 parameters. So once we have x of the centroid, y of the centroid, and theta, this is called pose of the robot. Okay, if we call it the vector, this is the vector of the pose of the robot in the workspace. Now, the equations that we want to get is between the time derivatives of these 3 parameters, x dot, y dot, theta dot, and what? The RPMs, or the angular velocities of the right tire and left tire, that here I call them phi dot r and phi dot l. Okay, so basically we want to go from the joint space phi dot r, phi dot l, to the workspace x dot, y dot, and theta dot, and we want to relate them together through a matrix. So to do that, we need to work through these 2 intermediate variables, v and omega. If I have v and omega, you know they are directly related to the derivatives of x, y, and theta. Why? Because derivative of theta, time derivative of theta, is directly omega. And then time derivative of x dot and y dot are what? Well, x dot is if this guy moves at velocity v, because x is x of centroid and v is v of centroid. So if you have v, it has 2 components, right? Cosine theta and sine theta. The cosine theta is vx, which is x dot. So x dot or vx is going to be v times cosine of theta. And y dot is going to be v times sine theta, correct? So these are the 3 relations between the parameters v and omega as well as theta to the time derivative of the pose components. And what I can do, I can write this relation into a matrix format that you can see up here. I can say I can multiply the vector by v0 and omega multiply that by this matrix, and this matrix, once I multiply it by V0 omega, should give me x dot, y dot, and theta dot, and that is true, because if we multiply, what do we get? We get x dot to be equal to cosine theta times v plus negative sine theta times 0 plus 0 times omega, so you definitely only get cosine theta times v, that's x dot, right? Then we can say now y dot is what? Y dot here is the second row, so it is going to be sine theta times v plus cosine theta times 0 plus 0 times omega, so you will get sine theta times v. And finally, we have theta dot, which is going to be 0 times v plus 0 times 0 plus 1 times omega, so theta dot equals omega. So what I can do, I can multiply the vector formed by v omega and an extra 0, multiplied by a z rotation matrix of angle theta. If you look at this matrix, definitely this is a rotation z matrix, right? So if I multiply v0 and omega by a rotation v matrix, that should give me the time derivative of the pose. Now the question is, what relation exists between these two intermediate variables v and omega to the angular velocities of the two tires, right? Phi dot left and phi dot right. For that, we need to look at the kinematics of the robot. So if you look here, I have 2 points on this robot. Let's say this point here on the left tire, I call it point B, and I have here a point on the center of the right tire, call it point A, and the centroid, I call it point C, right? So can I find the velocity of the centroid of A and B? Yes, you know, if they are rolling without slipping, V of centroid of the right tire is going to be the radius of the right tire, correct? Times the angular velocity of the right tire. The same thing applies to the left tire centroid. V of B is radius of the left tire times the angular velocity of the left tire. So these two are conditions of rolling without slipping for the left and the right tire, right? Now the question is, what is V of C? Well, V of C you can easily show it's the average of V of A and V of B. Why is that? Well, if I have this rigid body in general, and this is C, this is A, this is B, and they are mirror image of each other with respect to C. So V of C, as you know, is equal to V of A plus omega of the rigid body cross R of C with respect to A, correct? Where R of C with respect to A is this vector. Similarly, I can write V of C equals V of B plus omega cross R of C with respect to B, where R of C with respect to B is this vector. If I add these two relations together, I will get 2 V of C is equal to V of A plus V of B, and then plus omega cross R of C with respect to A plus R of C with respect to B. And what is sum of these two vectors? Clearly you see these two vectors are negative of each other, so this whole term is 0. And omega cross 0 is going to go away. So clearly V of C is what? Half of V of A and B, right? The velocity of the centroid is the average of the velocity of the centroids of the left and the right tire. Correct? And V of A, if you remember, it was radius of the right tire times angular velocity of the right tire. The same thing for left, it was radius of the left times angular velocity of the left divided by 2, correct? So magnitude VC, if we just want the magnitude of it, right? The magnitude of VC is clearly coming from this formula, right? R right, phi dot R right plus R left, phi dot left divided by 2. And that's exactly what you get here if you multiply the first row by the column of the joint velocities. That will give you B, right? Because here you can see when I multiply the first row by the column vector on the right side and add them together, that's the relation we just derived for V. So you clearly see that, right? That's what you have. Radius right, phi dot right plus radius left, phi dot left, the whole thing divided by 2. So the first row is that. Now what about the second row? Omega in terms of those phi dots. How do I get that? Again, I can get them from these two equations. But this time, instead of me summing these two equations, I'm going to subtract these two equations. So here, let me go ahead and write it somewhere else for you. So I write them again here, but this time I'm going to subtract. If you do VC minus VC 0, you will get here VA minus VB. And then you will get plus omega cross R of C with respect to A minus R of C with respect to B. And what is R of C with respect to A minus R of C with respect to B? So here we have to subtract the C with respect to A, C with respect to B. So we put both of them starting at the same point, like this. And negative means what? Negative means connect the end of the negative vector to the end of positive vector. So this is R of C with respect to A minus R of C with respect to B, correct? What's the magnitude of this vector? It is the distance between the two wheels, clearly, right? It is the distance between the two wheels, which here we call it 2 times B. Okay, the width of the chassis, we call it 2 times B. So if you look at the magnitude here, the magnitude of this guy is 2B. The magnitude of this one is omega. Omega and that vector are perpendicular to each other. This vector was in the plane. This is out of the plane. So magnitude of cross vector is simply going to be what? It is simply going to be derivative, it is going to be the magnitude of first one times magnitude of second one times sine of angle in between, which is 90 degrees, so it's 1. And here, if you want, you can take this guy to the other side. So magnitude-wise, omega is going to be what? It is going to be really V of what? It is going to be the magnitude of VA minus VB. Now here you have to subtract this way because you take them to the left-hand side, divided by 2b, correct? Magnitude-wise. So the magnitude of that vector, the difference between bb and va, divided by 2b, the magnitude of that is going to be what? Omega. So now here it depends on which one is bigger, right? But clearly it is going to be, for VA, we have to replace it with R of right times phi dot of right, and then plus R of left phi dot of left, divided by 2b. So this magnitude is magnitude omega. And that's why you call it differential drive, because clearly you see now the difference between the velocities of the two tire centroids is going to determine how you would steer. If they are moving at the same speed, there will be no rotation. If one of them is rotating faster than the other, there will be a rotation. Now the question is, which direction is the rotation? Well, it does depend on whether this entity is bigger or this entity is bigger, right? So to do that, we can look at here, see what happens. Well, if A moves faster, right? So this is your robot, and your right tire moves faster than the left tire, definitely your robot is needing to go counterclockwise, which is positive. So the positive direction for omega corresponds to the fact that VA is bigger than VB, or the right tire is moving faster than the left tire, then it is going to go counterclockwise. And if B goes faster than A, then the robot is going to go what? Clockwise, right? But does my equation show that here? Well, it comes from the fact of the direction here, okay? What does the direction tell me? Well, when we subtract it here, we had 0 equals VA minus VB plus omega cross R of C with CA with minus R of C with respect to B. If I take this term and bring it to the left-hand side, what do I get? I will get VA minus VB is equal to negative omega cross R of C with respect to A minus R of C with respect to B. So what are the directions? The direction of VA minus VB, as I said, for example, for this case where A is bigger than B, if we look at that here, what direction is that? The direction of that, since A is bigger than B, the direction of the subtraction is going to be aligned the XR, correct? Remember, this one was XR and this one was YR. So it is going to be so many units, whatever it is, in magnitude, and then in the XR direction. What about this vector here? We learned that RCA minus RCB, correct? So this was RCB, this was RCA. When we subtracted, it was in the YR direction. So this guy was whatever units that it was, which was 2B, and it is in the YR direction. Omega is in the ZR direction, right? If we assume it's positive. So negative of, and this was omega in the ZR direction. Now, do I get the right thing here? So it is like ZR times YR with a negative sign is XR. Is that correct? And we know if we had a K cross J, you know K cross J is what? Negative I. But with another negative, you will get what? You will get positive I. Correct? We know the system is a right-handed system, so this one is perfectly right. In other words, if we reverse the order, right? Correct? If we reverse the order or subtract basically the second one from the first one and multiply by a negative, what you will get is basically VA minus VB times XR. What we can write is the J vector cross that, so it is going to be R of CA minus R of CB cross omega. This way, this is J, this is K, J cross K is I. Okay, so to get rid of that extra negative that we have here, we can write it this way, and now magnitude of this is 2B, and magnitude of this guy is simply VA minus VB, or it is R right times phi dot right minus R left times phi dot left, and magnitude of this is omega, and sine of angle between them is simply sine of 90 degrees. So omega clearly is this entity divided by what? 2b, the VA minus VB divided by 2b, and that is exactly what you will get here. If you look at the second row equation, right? If you multiply this by phi r, multiply this by phi l, that will give you omega. R right phi dot right minus RL phi dot L, the whole thing divided by 2b, that's omega. So now I have related V and omega to the joint velocities. I also could relate v and omega to what? To the workspace velocities. So if I combine these two equations together, I can directly go from what? From the joint velocities to the workspace velocities, right? And that is done by this 2x3 matrix. So this guy is a 2x1. I need a 3x2, sorry, 3x2, not 2x3, and it goes to a 3x1. Right? So this 3x2 matrix can relate joint velocity to workspace velocity. And what was the name of it, by the way, if you remember? You're right. The name of this guy was Jacobian, correct? And these equations are your what? What's the name of these equations that you get here? Yes, they are forward kinematics, but not forward kinematics, because forward kinematics is between phi right, left, and xy theta. These are between their time derivatives. So let's see if you remember their names. Yes, you are right. The names are what? Differential forward kinematics equations. So the names of these equations are called what? Differential forward kinematics equations for the differential drive robots. And this matrix that is relating the joint velocity to workspace velocities, we call it the Jacobian matrix. You see, it depends on a few parameters: radius of each wheel, as well as the width of the chassis and the angle at each point. Okay, so this is what we have for the mobile differential drive robot. And again, the reason we call it differential is the difference here between the speed of the right and the left centroid tires determines the rotation of the chassis. Okay, so this differential drive robots can go forward, pure, if we do what? If we set phi dot left and phi dot right to be equal. If they are equal, then omega is clearly going to be 0, assuming that the radius of the two wheels are the same. If the two wheels have the same radius, then equality of left and right RPM means omega is going to be 0, and V of the centroid is going to be the same as velocity of each tire, or the average of the two. So this is going to be the same as VA, and it is going to be the same as VB, okay, or the average of the two. Good. So pure goes forward, and if you make both of them negative, right, both of them still equal, then it goes pure backwards. Then if the omegas are not equal, phi dot left and right are not equal, what's going to happen? Well, we saw that if phi dot right is bigger, it means what? So let me summarize it somewhere down for you so that you have it for your own records. So if phi dot right equals phi dot left and they are both positive, it means V is going to be, V of centroid is going to be the same as V tire A, going to be the same as V tire B, which is equal to phi dot times R, where these two are equal to the same phi dot, and the radius of left and right here, we assume they are the same radius. Okay, so if we assume that, then case 1 is they are both rotating about their axis counterclockwise, then the robot is going to move forward, straight line. Case 2, again, they are equal, but they are both negative. Then again, the centroid is going to move the same as the two tires, but it is going to move backwards. If one tire is going faster than the other one. What happens here? V is definitely the average of the two. And omega, which is the subtraction of the 2 divided by 2b, this is going to be counterclockwise. So it is going to be r phi dot r minus r phi dot l divided by 2b. Right? The robot is going to turn left, basically. Case 4, if phi dot right is less than phi dot left, but they are all again bigger than 0. So they are rotating in the same direction, yet left one is rotating faster. Again, V is going to be the same, so I'm not going to write it. Omega is going to be the same. I'm not going to write it, but it is going to be clockwise rotation, or it turns right. And there is a case that they rotate equal magnitudes, but both have or they have the different signs. So the case that phi dot right is equal to negative phi dot left. So one tire is going one direction, the other is going exactly the same RPM backwards. What's going to happen? V of the centroid is going to be 0, and omega is going to be omega max, which is going to be a 2 would cancel. You would get r phi dot divided by b. Okay, so if these two are equal to a phi dot or negative of phi dot, so this is positive phi dots, right? This other one is what? Negative phi dots, correct? Then this is going to be your max omega, and that is going to be r phi dot divided by b, and it is going to rotate in place. It's not going to move at all. It is going to pure rotation in place about the center, either this way or this way, depending on which one is positive, which one is negative. So these are all 5 separate scenarios, individual scenarios that can happen, right? Pure forward motion without any rotation, pure backward motion without any rotation, motion forward as well as rotation to the left, motion forward as well as rotation to the right, and no motion at all, just pure rotation in place. Okay, so these are all separate scenarios. And now before I get into this non-holonomic constraint that we have on this motion, which means basically not moving to the side, I want you to see a MATLAB demo and an animation that I wrote. So here I have my radius of each tire to be about 7.5 centimeters, the chassis width to be 30 centimeters, right? So 2b is 0.3, the simulation time 3 seconds, initial pose is completely 0, x, y, x naught, y naught, and theta naught. And then I use 60 points for the total simulation. I pre-allocate my pose, start them at the initial value, and then I divide my motion into 3 parts. In the first part, right tire goes faster, 240 RPM, versus left that is 120 RPM. In the second part, the right goes slower, the left goes faster, so right is 120, left is 240. In the last part, they both go the same amount. And here, so my command is changing, my phi dots are changing versus time in general. And here I do an animation. So if you look here, this is the animation part. In the first part of the motion, right tire is going faster, so you move and turn right. The second part, the left one is going faster, so you turn right or clockwise and you move. And the last part, that they're all the same, they're both of them the same, they go on a straight line, correct? So here, phi dot right bigger, here phi dot left bigger, and here they are both the same. These are the angles of the robot chassis, theta, right? In the first part where your theta right is bigger, you see your theta is increasing, right? It goes from this orientation, if you remember, the straight orientation. It goes to now goes on a circle, so now you're lifting this way. Then when you go back, now you reverse it back to 0, and then you don't change it at 0, which is exactly what you see here if you look at the plot of the angle of the chassis, right? And if you also look at the commands here, you can see them. Phi.right is in blue, phi.left is in red. So first right is bigger than left, then left is bigger than right, then they are both on the top of each other. So you can do whatever type of simulation that you want in here. Okay, here just to make it a little bit more interesting for you, I changed the last part of the motion to negative 120. So now it turns to the left, then it turns to the right. In the last part, they are rotating in the opposite direction with the same RPM, so it should only do rotation in place. So let's take a look at that. So here we go. This is the part that it is doing pure, it is doing rotation to the left, counterclockwise here, and now look at the last part. You see, pure rotation in place. So you can do whatever experiment that you want with this code and simulate the behavior of the differential drive. Now, as I said, these differential drives, they have a major limitation called Non-Holonomic constraint. And if you want to first describe it in plain English, the meaning is this: they cannot move sideways. Okay, that's the simple meaning in English. They cannot move sideways. How can I tell? Well, here, if I ask you what is y dot of r, correct? Right? How is the y component of the body attached frame yr is going to change with respect to time, y dot r, right? That's the lateral motion of the chassis. How can you find it? Well, you say if I have x dot and y dot, correct? Then y dot cosine theta minus x dot sine theta, it is going to be y dot r. Well, how is that? Let's take a look here. So remember that the angle of yr with respect to the x and y is 90 degrees plus theta, correct? So if we take a look, in general, this is my object. This is the axis along which I want to project the motion. And in general, this v that I have, correct, it has a vx motion and a vy motion, or it has some x dot and it has what? Some y dot. And this angle here is theta, basically, or the angle between, as I said, yr and the x-axis is 90 degrees plus theta. So now how would you decompose x dot and y dot along this yr? Well, it's clear. For y dot, it is going to be y dot cosine theta, correct? And then for x dot, what is it? It is going to be this projection, where you need this angle, and this angle here is 90 degrees already, that's theta, so this angle is 90 degrees minus theta. And so it is going to be cosine of 90 minus theta, which is what? Sine theta. So this is x dot sine theta, and this is y dot cosine theta. And you see the y dot cosine theta is in the positive yr, x dot sine theta is negative r. So your total yr dot is y dot cosine theta minus x dot sine theta. But what is y dot, what is x dot based on these equations that we have, right? Your x dot is half of the radius cosine theta phi dot r, and half of the radius times cosine theta phi left. So if you plug it in here for x dot, and then for y dot, similarly, it's half of the radius sine theta r phi dot plus half of the radius sine theta the other phi dot. So if you plug in x dot and y dot from the top equations and factor out sine and cosine, if you simplify, you'll see the result is going to be 0. Why is that? Well, if you just do it, what's going to happen here? If you factor out phi dot r, what terms would you get? Here you have r over 2. Let's assume the r's are the same. They are all r. Okay, so they are all r. So the phi dot r is going to be what? It's going to be r over 2 sine theta cosine theta. And then you have a term here, which is negative r over 2 sine theta cosine theta. And then our cosine theta sine theta, that's the same thing. And if you do the same thing for phi dot left, you would also see again here, you have r over 2 sine theta cosine theta. And then on the other one, you have minus, again, r over 2 cosine theta sine theta. Right? So clearly, both of them are going to be 0, right? Summation of them is 0. So it means in the y dot r direction, there is no change, there is no velocity. So this differential drive can never move sideways. And we call it a non-holonomic constraint. Why is that? Or what is that? It means it cannot be integrated. Integrated into what? Well, your constraint right now is y dot cosine theta minus x dot sine theta, correct? Which you can also write it as a matrix format if you want. You can write it as x dot and y dot, correct? And then you have to pre-multiply that by sine and cosine, correct? So you should write it like this, negative sine theta and then cosine theta. So you can write it like this in general. This is equal to 0. So this relation is between the pose velocities, between the workspace velocities. Can you go ahead and integrate this with respect to time and write it, instead of writing it this way, write it as a relation between what? X, y, and theta to be equal to 0, right? So instead of the workspace velocities, write the constraint in terms of the workspace variables themselves, the pose variable themselves, without the velocities, just x, y, and theta. If you can do it and write it back in terms of x, y, and theta, in general, the workspace variables, we call that a holonomic or integrable. If you cannot integrate it with respect to time and write it this way, which in this case you cannot, we call it non-holonomic or non-integrable. Okay, you cannot time integrate that. So you have to leave it as a velocity constraint like this. In general, any velocity constraint that is like a of q, correct, times q dot equals 0, where q is the joint variables or the workspace variables, and q dots are the same thing, the velocities. Any constraint that is like this, we call it a Pfaffian constraint. And holonomic constraints are a group of non-holonomic constraints. Non-holonomic constraints are a group like this. Okay, in general, if we can convert these into a simple relation like this, f of q to be equal to 0, then we call them what? Holonomic. If we cannot integrate it into that form, we call it non-holonomic. Okay, so in this case, we cannot time integrate this relation. Therefore, we call it a non-holonomic or non-integrable constraint. So this is everything about the kinematics of a differential drive robot. And I want to explain this odometry that I mentioned in video number 1. I mentioned it in several places. Let me explain it and then I finish this video. So what is odometry? Remember, I said it's a dead reckoning. It's counting in which direction and how far, but by how far I mean you can count the time and the RPM of the motors and then estimate in which direction, how much of distance you have traveled, how much you have rotated, and so you estimate your pose values at any time, x, y, and theta of t. Okay, so the odometry, if we want to describe it properly, this definition comes from the book by Professor Lynch from Northwestern University. His textbook is, by the way, amazing. He wrote a very good textbook, and I absolutely recommend you take a look at his textbook, Modern Robotics. Some of the pictures and formulas in this textbook, in these videos, are coming from his book. Some others are coming from the book by Spong. Okay, in general, these two are very good textbooks for robotics. So here, all you are doing really is you have these time derivative equations, and you apply a finite difference and do some approximation to get the odometry equations on the right hand side. So instead of x dot, which is the limit of delta x over delta t as delta t goes to 0, you choose a small delta t, and so you approximate it by delta x over delta t when delta t is really small. And for delta x, if you use backward difference, it is going to be x at current time minus x at the previous time that you have, and divided by delta t, and that's exactly what you see here, right? If you cross multiply this x dot and this right hand side of here by delta t, you will get x dot delta t equals x of t minus delta t. If you take this term also to the left hand side, that's exactly this equation that you will see here, where this product here is basically the equivalent of x dots, the product of the first row and the column. Okay, and then you do a similar thing for y dot. You write it as delta y over delta t, theta dot delta theta over delta t, and you get these recursive or update equations that you will get here. And you can start at time of 0. At time of 0, you have your x, you have your y, you have your theta. So you know this value at time 0. You know the x and the y at time 0 and theta, as I said, and then this t is going to be at time delta t at the next sample point. And you can calculate those if you know the angular velocities at time 0 or at any point in general. So if you know the angular velocities of the two wheels, you can integrate them and get these. Now, many times your angular velocities are not directly given from your encoders to you, because not all encoders have velocity feedback. Most of the encoders only give you an angle. They don't give you an angular velocity. And if that is the case, then you have to change these equations to be only using the angles from the encoders and no angular velocities. And so if you modify them, you will get these equations here on the right hand side, which are almost the same as or identical to these guys, except they're based on the angles. So here phi r and phi l are direct angles read from the left and right encoders. You subtract them, multiply by r divided by 2b, that gives you the chassis angle. And if you look at the change in them from the previous time to the current time, right, and incorporate them into the top formulas, that will give you delta x and delta y, or add it to the previous x and y, it gives you current x and current y. So delta phi r here means the phi r at current time minus whatever you had at the previous time. Okay, so you need to keep track of the last value, okay? When you read a new value, you also need to keep the previous value so that you can calculate these deltas. So do not keep cleaning all of the history during your odometry loop. You need to keep track of your last value. That's why in MATLAB, whenever people use Simulink for the purpose of odometry simulation, they use the memory block. If you have seen many people use this memory block, which keeps the last value of the signal. Okay, so that's a very useful block for odometry, this memory block. But in general, this is the odometry equations, if you have velocity feedback or you don't. Now, the main problem with this dead reckoning or odometry is drift, which means the estimated path is gonna be deviated from the actual path over time. And in reality, it comes from two major problems. One is the slipping under the tires, because these equations that we have, they are all based on pure rolling without slipping under the tires. And if there is any slipping, these equations are not going to be completely valid, right? There will be some changes. That's one. The other thing is this approximation that we did. We approximated x dot, which is dx over dt. We approximated by delta x over delta t if the delta t that we use is very, very small. In reality, this delta t is not super small. It is depending on how fast the system can get the data from the encoders and how fast it can process them, right? But it is not really nanoseconds or microseconds or picoseconds or so on. It is typically in the order of milliseconds, sometimes close to a second. And so that's where this approximation, this finite difference approximation, is going to have some error, and that error would accumulate. So here, since I don't have a robot right now handy and a mechanism to show its actual path, and then I estimate the path and show you the problem of accumulated error, which is this one, I can simulate for you the problem of slipping. So what I will do, I simulate these equations for you, but I add a percentage of slipping in under each tire to show you what's going to happen. And that is what I have in this code. So I show you separate scenarios here. Scenario 1, there is no slipping under any tire. Scenario 2, there is 2% slipping on the right tire. Scenario 3, there is 2% slipping under the left tire. And I show each one of them in a separate color. So here, if I show you, the one in bold red font is no slipping case. So it is the same path that I used in the previous simulation, turning left, moving forward, turning right, moving forward, and going straight. Then I change it where in the black one, right tire has some slip. So right tire is not going to move as fast as we wanted. There is a 2% reduction in the speed. So instead of, for example, V at the center of the right tire to be exactly R of the right tire times omega of the right tire, it is this number times 1 minus the slipping percentage, right? So if it's 2%, it means only 98% or 0.98 of this number is going to be transferred to V8. 2% of it is going to be pure rotation in place. If that's the case, right, my right tire is moving less than what it should, and instead of my robot here moving on this path properly, my left tire is going to go faster than expected, right tire less. So my car is going to be tilting to the right. It is going to do a little bit more clockwise rotation, and that's what you see. This this black curve is on the right side of the actual curve because there is a slipping on the right side. On the other hand, if I do slipping on the left side, the right tire is rotating more than expected compared to left. So my car is going to rotate a little bit counterclockwise, and you see the green curve to be on the left side of your actual curve. Okay, so here I'm just showing you the scenarios of slipping on each one of the tires versus no slipping, and the path that are generated. You see clearly the deviation between them, and the more simulation time it goes, the more the deviation would be, and the slipping will cause the actual path and the desired path to be drifting apart. So here I can show you the slipping problem. If I had a robot, I'll try to make it in future videos. And if I have a mechanism to actually have the desired path versus estimated path, I'll generate this kind of curve as well for you. But you clearly see the deviation in here. That is the odometry problem. So whenever we do odometry, and we use encoders, let's say for mobile robots, we need to have a separate mechanism to fix for this error over time. And that can come from vision, that can come from GPS or any type of other sensor that I can rely on their point estimates at specific points, and I know their error does not accumulate, right? So if GPS can tell me here my exact location here, maybe here, 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 and here, not all along the, because GPS is not as fast as the encoder is, then by having these estimates, I can have a batch correction. I can use, for example, a sensor fusion algorithm like a Kalman filter and try to correct this drift over time and avoid it to get bigger and bigger, right? That's why odometry, as I said, is always accompanied by another type of sensor without accumulated error that I can rely on and avoid exponentially large drifts. Okay, but in general, this is the formulation of odometry. This is the drift problem. And we also looked at the kinematics of differential drive robots and the meaning of holonomic and non-holonomic or non-integrable constraints. So hopefully the video was useful to you. I will see you in my next lecture when we talk about omnidirectional wheels. Thank you.